submitted the this assignment. Let me check the for the quiz for the quiz stress. Okay, 2 students haven't turned in yet. But got one actually who today just now is wait, let me check.
Aku bagi link ni Stream Zul.
So Siti Haisa is not here, is it? Let me check. Siti Haisa, is it here? Okay, Siti Haisa not here lah. So still got one student haven't submit their assignments. Submit assignments. Suppose 28 students for quiz. Sorry, not the quiz. Quiz because Siti Haisa got get the permissions. Because she can't get the internet. That's why this morning she cannot join the class. She got actually send the SMS to me therefore she can't go to the town. That's why because of the flooded. Okay, so that one no choice allowed. But the other one, I don't know who did not submit here. Who did not submit? I believe still got one student, so I have to check it. Only know who haven't submit the quiz. Okay, I will check the times. Okay, take home quiz. So the rest already submitted. Okay, for this afternoon, we are going to discuss the last chapter of precast concrete design, which is the precast concrete joint, the connections. It's a big topic. I think at least I need to take 2 weeks to finish up these topics. 2 to 3 weeks. 2 weeks, at least 2 weeks. I have and have given you the lecture notes already share with you all. I divided few parts. So today we focus on the overall what type of precast connections, and also the we are focused on the calculations, focus on the bearing, focus on bearing. Then the second parts, next week we'll discuss another 2 types of the especially at least 2 types of the connections, which is the corbels and nips. Corbel and nips. And then I'm thinking actually to discuss the half joint. Okay, the half joint. Okay, half joint. So Chakra already joined. Okay, so still have 3 students haven't joined. I think minus Siti Haisa. So suppose have at least got 2 students haven't joined. Okay. And today I will give you an assignment. Assignment for
main
the
GTA
last
dengan
assignment for
PUBG.
precast.
Nampak muka dia?
I have scheduled it. I'm not sure whether already posted or not. Okay, let me check. I think I scheduled 4:30. If not mistaken, I scheduled it 4:30. 5 o'clock. Okay, 5 o'clock. Once come to the time, then I will explain a bit of the assignments. The assignment is something to do actually is related to your steel design. It's related to these topics, but something that you need to use the knowledge that you learn in the steel design to do the design to do the design of the connections. Okay, so Siti Haisa, Siti Haisa, you already joined here. Siti Haisa, are you okay? Siti Haisa dengar saya tak? Boleh dengar tak, Siti Aisyah? Okay, macam mana you pagi cakap flooded lah? Banjir. No line ya. No line. So, you punya apa? Ya, banjir ya. Okay, so dekat sana macam mana? You punya dapat buat tak yang dah hantar tak yang untuk quiz? Untuk quiz macam mana, Siti Aisyah? You ada hantar tak? Submit tak? Sudah? Okay. So, tak tahu siapa yang tak hantar lah. Okay, tak tahu siapa yang tak hantar. So, you dah bagi tahu saya, you dapat hantar. But there's 2 students did not submit. Saya tak tahu siapa mereka. Okay, so no problem. So, let's start our class lah. Okay. Okay. So, let's start the class now. I know it's afternoon, sometimes a bit tired also. A bit tired. Understand, don't worry. Okay. Can you record the class? Okay, sure. No problem. Okay, no problem. I will do the recording. Let's start now. Okay. Wait, before this, 21 students. Okay. 21 students.
Apa je? Tidur. Sekejap lagi tak keluar meeting. Doktor tunggu je.
Okay,
Ya apa?
good afternoon,
Are you
everyone. Okay, so before we start our lectures, got another things that I would like to discuss is regarding the test. The test. I think last week that we have done it last week. I haven't looked at I haven't marked actually. I haven't marked. But I would like to explain to you regarding the question number 1. Okay, question number 1, how to solve it. And because question number 1 is a bit, not say tricky lah, but you have to go back to your fundamental to do the design to solve this problem. Okay, so you look at here in these questions. Question number 1, actually, this is a precast column. This is a precast column, and at the end here, okay, the length is 10 meter. Okay, the length is 10 meter lah. And the size is 750 mm square. Okay, so this one, it mentions here, this column, we are going to design the hook here. Means we are going to check the hook and giving you the tensile strength of the R16 hook. Okay, and also the partial safety factor. Okay, the partial safety factor. And the column is going to lift out with a 45 degree. 45 degree. Suppose I think the hook, suppose actually, if let's say I draw a bit, follow the 45 degree will be much better, but it's okay. It's okay. So it's going to leave it this one. So now asking you, is it this R16, is it passed or not? Okay, is it passed or not? Okay, it's another one submitted take home quiz. Who? Okay, so ask you to solve to get this one. So basically, in this kind of situation, you need to get actually what is the force applied, and if you leave out, basically this is will be in tension, and there is two leg here. Okay, we know all the bonding and so on. We assume the failure is on the whether the tension capacity of the R16 hood is sufficient or not, and giving you the what is this? The strength. Okay, the tensile strength 250, and partial safety factor for steel hook is 1.15. Okay, so how to solve it? Actually, how to solve it? This one, how to solve it? Okay, how to solve it? Actually, it's very straightforward. For you, actually, this is very straightforward, huh? And for me, lah, the solution is not very long. The solution is not very long. So basically, this one is something like if we leave it out, okay, if we draw out the free body diagram, if we draw out the free body diagram, if let's say I can show you the maybe the answer scheme. Test 2. Yeah, let me check the answer scheme. So basically, if we draw out the free body diagram here, okay, first of all, you have to calculate the weight, the weight of the of this under ultimate limit state. You have a 750 times 750. Okay, so multiply by the dense unit weight of the concrete, and then we multiply by the length, so we get basically, and multiply with 1.35 is a factor of 1.35 GK factor it. So basically the weight here, total weight of this column is 190 kilonewton. Okay, 190 kilonewton. So in this kind of station, so now if 190 kilonewton here, and we are actually is pull out with a 45 degree here, pull with a 45 degree. Okay, so now basically what we want is to get the T here, the tension force. The tension force. We know it's in this directions, so we can derive, okay, with the components. The same T cos 45 and T sin 45 because this is 45 degree. Then we can go use the static dynamic to get the reaction here. Okay, I resolve from here, I resolve into 2. The way I did is I resolve into 2. Okay, resolve into vertical and horizontal components. So at the end here, at the end, basically I can solve to get the T, okay, T. So basically when T apply here, so you're going to divide into, this is the force that we're going to pull it. Okay, whether the hook here is the capacity of the hook here, the R16 hook, okay, with 2 legs, so whether it's sufficient or not. So we give you the strength. So you have to calculate the means that for 16 mm, we got 2 legs, is it? 2 legs. So therefore 16 mm is 201. So basically it's 402 and then we can calculate the capacity or the tension capacity. Is the cross-sectional area multiplied by the strength divided by the plasticity factor. So you look at here, the capacity is only 87.4. Okay, 87.4. But 87.4, but the force, the tension force that we're going to lift it out actually is 134. So basically it's not pass. Basically it's not pass. Okay, so this one is go back to the fundamental, give you some idea. But the second questions I haven't prepared because I already changed the questions. I already changed the question for second questions. Okay, so this is about the test 1, test 2, sorry, it's a test 2. It's the test 2, the solution of the first question. So now we continue with our lectures of last topics. Okay, precast concrete joints and connections. Okay, you look at precast concrete. Precast concrete, you look at the elements, basically is something like puzzle by puzzle, pieces by pieces, is it? Then after that, we are going to join it. Therefore, the joint is very important in precast concrete constructions. Okay, the joint, the connection is very important. We will make sure that you're able to join. For example, let's say in between the column and the beam, how we're going to join it. Okay, between column and column, between if the column, precast column to the foundation, how are we going to join it? And if you are design the column to the base is fixed or pin, then how you need to provide type of joint you need to provide. So and the joint, the purpose of the joint is to transmit the forces between the structure members. It means that if they say it's beam, main beam, secondary beam to the main beam, so we have to make sure that the connection between the secondary beam and the main beam able to transmit the force from the secondary beam to the main beam. Okay, if between the beam to the column, so you have to make sure that the forces on the beams able to, the joint that you make able to transmit the force from the beam to the column. So, and this is one of the main function. Other than that, you must provide stability. Okay, you must provide stability and robustness. Okay, these are the functions, the purpose of a joint in precast concrete. Okay, not only in precast concrete, like if you look at others like steel design, also the same. Steel design also the same. These are the main functions of the connection. Okay, so how to make it? How to make this kind of joint? So we can use what? We can use bolting, we can use welding, we can grout it. Okay, as simple as possible lah. Okay, we try to make the joint as simple as possible. Don't make it very complicated. Okay, so now we look at let's say example of precast joint or connections between the column and the foundation or the base here. Okay, we can just slot in only column in grouted pocket, means slot in then we grout it. Okay, or we can just sitting on the base or the foundations. Okay, then we have a shoe, we have bolted, then we have a shoe or brackets. Okay, surrounding the column. Okay, we can have a grouted sleeve. Okay, we can sleeve here, means we got the hole, then we can slip in. Okay, then we can grout it. Okay, then we can also actually do it something like using the base plate, something like in steel design. Okay, steel design, this one also can. Okay, this is the column between the precast column to the foundation or the bottom parts. You can even this can be as a footing, or it can be even is as a slab. If that say is sitting on a ground floor slab and so on, you can not necessarily is a footing here. Okay, so between the beam to column, we can like
Hello?
beam to column face. We can have something like
What?
slot in, or we can actually, this one is a corbel. Okay, it's a corbel that we are widely used here for corbel. It's one of the next
Kau
week we'll
record
discuss this one, corbel design, how to design this corbel. Okay, we can have actually the column haunch here. Means the column here, this is the bigger size. Here there's a haunch here, then it's sitting on the haunch. Then we have the dowel bar here. Okay, we have dowel bar here. Okay, so, this one not necessarily we have a dowel bar. Sometimes it's just sitting on it only. The beam on the this corbel. Okay, so then between the and this is a shallow corbel, something like this. We name it as a shallow. We can go have a deep corbel. Okay, go use the deep corbel, something like this, directly going deep corbel. Okay, my undergraduate students final project once okay, actually got joined our lectures, just joined the class for pre-stress. She's doing this one, the shallow, and doing the design of the corbels to establish to produce the design table. Okay, and also after that is to look at use the FEA finite element analysis to look at the effects of if we the shear span. After that we see the shear span over the effective depth, the effects on the shallow corbel and deep corbel have to do simulations. Okay, so between column to column. So if let's say the column to column is very long, we cannot make it one in the single column. So we have to join it. So basically we have to go to use the splice connections, splice connection. Okay, so we can do something like this also. Here, the join something like this. Okay, make this one a half join to column arms, to column arms here, half join. So this is called half join. So the beam here, these are the half join here. So I'm thinking actually to discuss also to include this one in our as one of the join that you are going to learn. Okay. What else? So now these are few types of joint connection. So now we look at, if that say is the bolted column to column connection, how it look like. Okay, we're using the base plate. Okay, the reinforcement is something like this. Let me check the got anything important or not. Okay. 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 So something like this. Okay, this is a base plate, so we can look at it. How is it? We make it. And between the column to column, we're using the sleeve. Okay, basically we are going sleeve in, then we can grout it. Okay. Then beam to column connection, this some we're using metal connection and so on. Then using cobell, if let's say sitting on a cobell. Okay, if let's say using pre-stress and so on, post-tensioning. Okay. And there's another one actually we call it as a nips, that the especially the precast slab that's going to, if that say precast slab can sit directly on the precast beam, but they have also, if that say want to make the same level, means we can from the beam here we can project a short cantilever, that this short cantilever is going to support the precast slab. So that parts we call it as a nips. Yeah, that one is in our syllabus. In next week we'll study it. We'll look at how to design. It's just a short cantilever, not very difficult to design. That one very straightforward. Okay. So if that say the beam to column, we can, if directly sitting on top, we can just slot in. Here there is a bolt here or bar, then there's a hole here. We can direct sitting on top and provide with a bar here. Okay. Okay, so we look at some problem or challenge of precast concrete connection. Sometimes it's very difficult, especially you got few type of these precast elements. So become the joint become very complicated. And sometimes it's because of the we can have, you that say not proper design. So if it's subjected to any load and during the installation and so on, so it may have some failure happen. Okay, so another one, if that say not proper constructions, here you see on the left hand side on this picture, on the left hand side here, this one the bearing is not sufficient. Bearing is not sufficient. But however, if let's say look at this right hand side here, this one the bearing is too much of bearing, excessive bearing length, also not good. Let's say excessive bearing length here, so it cause here the stress here, develop the stress here, and cause the crack happen here. Okay. So now we look at the forces of precast connections. Actually today maybe not very long, there even the lectures target to just cover the first part only. However, if let's say we have extra time, then we have we can discuss a bit of the second part. Maybe not touching the calculation, we just look at some theory. Okay. So if you look at the connection here, if you look at connection here, for example, the connection here, this is a column. Okay, we have a short cantilever come out, then there is a bolt here. Okay, and this is the beam. You can consider this a beam. Okay, rough. Basically you will see this will be under compression. If let's say the load apply here, this will under compressions. So on top this part, this will be under tension. Therefore, the joint, the connection here, the behavior you can predict. You should understand the behavior is the same, almost the same as what the connection in the steel design. Okay, when apply the load, how it look like, how it's going to behave is important. You have to know whether it's compression, tensions, and is it got shear and so on. So you have to understand. You have to understand. Then you can design for it. Okay. So now, today the target here is design of the bearing. Design of the bearing. I will show you the example here is based on Eurocode 2 lah. But actually, initially I'm trying to prepare the example in BSA 1 because BSA 110 is very straightforward for the bearing. Very straightforward.
Tak bagi tahu dia
I
tadi.
have included in the notes. Okay, include in the notes. Sometimes I don't like Eurocode 2. Why? Too detailed here. In this case, too detailed. But however, actually, we can simplify. If you look at the BSA 110, actually, it's very straightforward. Very straightforward. Give you a very straightforward. But at the end, you'll get about the same. You see, you'll get about the same. So basically, if you look at bearing here, for example, let's say this is a column. This is a column, and this here come out, there's a cantilever come out. Okay, whether this is a corbel or it can be a nips, okay, or it can be a haunch. Okay, our concern is this is what is the length here that we need to provide. Okay, the bearing length that we need to provide here. Okay, we need to provide. So basically, what to say? I don't know whether this one is correct or not. But this LB suppose is from the edge here to here. But never mind, it's okay. So basically, it's based on here. We are required. Yes, it's here. Okay, this is a gap. Okay, the bearing length here. In this case, we call it a length. It's basically refer to A1. You look at A1 is this one. Based on the plate. If that say that is a bearing plate here. Okay, there is a plate here. Okay, so there's a dimension A1. If that say without the plate, there's a way to calculate. So basically A1, remember, this is A1. Okay, then plus A2, A2 here. A2 here, and there's another one is the delta A2. Okay, A2, and then plus another one is the A3, and plus delta A3. Okay, plus delta A3. So basically, the length, the bearing length here is refer from here, the edge here, until the end of the beam here in this case. So it's A1 plus A2 plus A3 plus I can say plus delta A lah. Okay, delta A is combined between delta A2 and delta A3. Not just combined, it's just square root delta A2 square plus delta A3 square. After this, we'll look at it. So now the bearing, you have understand the fundamental already, and you understand the fundamental already. Basically, is we are going to get all this A1, A2, A3, and then you have to provide sufficient the bearing length. Means that you're a beam or whatever. This can be a beam or this can be a slab. Okay, a precast slab. Then sitting on the short cantilever here. So what is the minimum length here that we need to provide? Okay, this is the gap lah. We not consider the gap here. Okay, we must have gap, means we need the tolerance. Is it? Sometimes the gap here is for us to if you want to do grouting, or if you want to make sure that during the construction you can stop. If you are not going to design perfectly, if that say there's some discrepancy or some error casting of the beam. If let's say you do perfect without the gap, what happened? You cannot slot in, is it? You cannot slot in. So there's a problem. And also when you make the column and so on, you may have some mistake, is it? So therefore we need a gap here. We need a gap here. So but our concern here, this one is overall here. So the A basically is the bearing length. We actually call it as LB lah, bearing length LB plus the gap G here. Okay, we get the total length here lah. Okay. Okay, so this one is for the A is if we are using concrete bearing here. Okay, if let's say we are steel plate, if let's say we provide a steel plate, the same thing here, but it's only here how to calculate here is a bit different only. Okay, if we provide a steel plate here, okay, there's a we have B1 plus delta A2 lah. Huh? Okay, so now we look at one by one actually how to calculate this all A and delta A. Okay, the ultimate bearing stress. Okay, imagine that the elements, okay, the precast elements when putting sitting on the supported elements here, so you produce a stress here. So the stress basically is the reactions, okay, of this precast element divided by the what? Divided by the effective bearing length. Okay, just now we say effective bearing length A1 plus A2 plus A3, okay, and also plus delta A. Okay, we get the effective bearing length multiply by the net bearing width. Multiply by the width, is it? So basically this one you get. So force divided by this is become an area, is it? The bearing area lah, huh? So we get the ultimate bearing stress, and this ultimate bearing stress must smaller or equal to FRD. Okay, and so what is FRD actually? FRD is the resistance, basically it's the resistance, is it? This one is the applied bearing stress. So FRD is the resistance. So the resistance here basically is equal to this, according to Eurocode, is equal to this is for dry connections. For dry connection means that dry connection is without bedding material. Means most of the time, let's say you are the concrete column, the concrete slab or concrete beam here, you are directly just sitting on top of the supporting elements only. Is it? So so that one we can consider as a dry connections. Consider as a dry connection, and is equal to 0. The resistance is equal to 0.4 FCD. FCD basically is FCK divided by 1.5. 1.5 is the FCK divided by the gamma partial safety factor. In this case, if you refer to the partial, means the FCK divided by gamma M. Gamma M in this case is 1.5. Okay, 1.5. I think so. Yes, 1.5. Yes. Okay, 1.5. So therefore, if you calculate, basically at the end is 0.266. 1 over 1.5, 0.67. Okay, multiplied by 0.4. Okay, so yeah, correct. Is basically 0.4 divided by 1.5 lah. Okay, 0.4 divided by 1.5 times FCK lah. Okay, so we get the 0.266 FCK. So this is the resistance. So we calculate this one. Basically, we have to make sure that it's less than this resistance. So sometimes if let's say you don't want to calculate, make it so difficult, you can just propose the length and so on, roughly get it, then you can make it conservative, and then you check whether the stress here, okay, the bearing stress, is it less than this value or not, 0.67 or 66 FCK. Okay. and the average bearing stress between the plane surface should not exceed 0.3 lah, okay, should not exceed 0.3. So basically, if you remember these equations, okay. So A1, so just now we mentioned that we want to get A1. So A1 actually, just now I got show you in the diagram here, A1 here. Basically, A1 is FED divided by FRD multiplied by LW, is it? Okay. So this is the design force divided by FRD, if we know this one, FRD, this one is it. LW is the bearing width, mean the other directions. Okay, what we look at just now is the bearing length. So perpendicular to it is the width. Okay, what is the width that we need to provide? So the width here got give a suggestion here. The bearing width perpendicular to the span, okay, LW bearing width is equal to B, okay, equal to B minus 2 times the largest cover to link in the supported or supporting member, okay, or 600 mm if no bedding material is used. B is the breadth of the member. Means that if they say this is the what, the member of the beam, okay, so it's going to sit on, let's say this is a supporting beam. So this is the connections here. So this beam, precast beam, is going to sit on it, part of it, is it? Okay. So these are the length. Consider this is the length. This is the length. Okay, effective bearing length, and then this is the width. This is a width. Okay, this is the width. So the width we name it as a LW. LW. So the LW is the B. If that say B, this is B lah. Means that this is the B. Okay, let's say this is 300 mm. So this is 300 mm minus 2 times the largest cover, minus 2C lah. I can say 2 cover. Let's say the cover is 30 mm. So 300 minus 2 times 330. So minus 60. Minus 60. So 300 minus 60 become 240. Okay. Or the supporting member, let's say a supporting member is not critical, or 600 mm, whichever is the smaller lah. Okay, in this case, just now I show you is basically is 240 will be governed in as the bearing width. So this will be the bearing width here lah. Okay, you see how after this we look at the example, you will get understand. Okay, so this is A1. So and the nominal bearing length, just now I mentioned is the bearing length is the A1 plus A2 plus A3 plus the delta A here. Okay, this is the bearing length lah. A1 plus A2 plus A3 plus the delta A lah. Delta A is delta A2 square plus delta A3 square lah. Okay, so this one, the bearing length here, usually we are going to round up to the nearest 5 mm. For example, let's say you get 161. Okay, you get 161. So you are going to round up to 165. Okay, you're going to round up to 165. You're not go to lesser. That is the minimum already. You can have to put it extra a bit. So you get 162. Also, you put 165. Okay, if you get 167, you're going to round up to 170. This is the meaning here. Okay, so now we already get the roughly we really get the A1. We already know the A1, how to get the A1 here already. A1 basically this equation already. Okay, so now the A2, delta A2, A3, delta A3, how are we going to get it? Okay. So just now I mentioned for the plane bearing, the in compression, let's say in compression, this one must be less than for bedded material. This means for the material that we're going to do the bearing, we have to make sure that we are not greater than 0.567 FCK. Okay, where FBED is the design strength of the bedding material. Okay, this is extra information. So basically the resistance here is the FRD LWA1. Okay, never mind this one. Now look at a minimum value. Okay, just now give you the idea is something like this. In theoretical is something like this, but if in the design how we are going to do that. Okay, so these are the table provided in the Eurocode 1, Eurocode 2, okay, part 1, okay, Eurocode 2, part 1. So basically, we can obtain the, we can get the value of A1, okay, by using this table. By using this table, means that we need to calculate the sigma ED over FCD. Okay, sigma ED over XCD, and we have to know what type of load that is going to apply on the bearing, okay. So either it's a concentrated support or if a line support is a rib support, then is let's say less than 0.15. Okay, so A1 you can take as 90. If that say is a concentrated support, you directly take 90. Okay, if that say it is a between 0.15 to 0.14, you use 110. If greater than 0.4, you use 140, something like this. Means that we are no need to go back to this one. We can just direct take from the table. Okay, take from table. You see how after this in the example how we are going to do that. Okay, so after that is the A2 and delta A2. A2 and delta A2 is taken, we can get it from table 9.3. Okay, supporting material. So what type of supporting material? For example, let's say precast concrete assumes FCK greater or equal to 30 megapascal. Okay, either when this is a line load or when it is a concentrated load. Okay, so when it is a concentrated load, for example, in an example, let's say the sigma ED over FCD is between 0.15 to 0.4, we use A2 equal to 15. And the delta A2, you are in this group, you can use here, either 10 mm or L over 1,200, must less than 30 mm. Okay, we are going to choose the value here. Okay, the delta A2. Okay, so table 9.3 basically for us to estimate the A2 and delta A2. Table 9.2 is to get the A1. Okay, A2 just now the A2 here. Okay, A2 supporting member example, the tips of the corbel in 9.5, where band bar, lift and so on. So, but basically give you an idea The A2 is the value for concentrated support. A2 is roughly between 15 and 25 mm. Okay, 15 and 25, in between 15 and 25 mm So this is for A2. If you look at here, the value here basically is from 15 to 25, is it? Okay. For concentrated here, roughly you will get 15 to 25 here. But it depends on the stress also, can be further reduced. Okay, so it just now already given 9.3. 9.3 already given. Actually, I have repeating this one repeated already. This is A2 and delta A2. Okay, so actually just now read there. This one repeated. Okay, repeated. That's okay. So now after this is the A3. Okay, A3 and delta A3. Okay, A3 and delta A3. Okay, A3 and delta A3. Okay, A3 is from table 9.4 here. Okay, A3 is from table 9.4 here. Okay, so basically if whether it's a line support or it is a concentrated support okay, or it is a concentrated support. So basically give you the value here. You can read here okay, A3 A typical value is actually A3 is 15 mm. Okay, it's 15 mm. Yeah, that is the typical value for A3. Okay. Okay, so now you look at delta A3. We still have another one is delta A3, is it? Delta A3. Delta A3 for length Ln of the supported member means the beam or the slab, how far is it? Okay, the supported member is, you can, from here we can, from the length of the supported member we can estimate the delta A3. The delta A3 is the length of the supported member divided by 2,500. Okay, 2,500. If they say it's a 6 meter, you can 6 meter divided by 2,500. Okay. So after you get the delta A2 and delta A3, basically we can calculate the delta A based on cert delta A2 square plus cert and delta A3 square here. Okay. So maybe you see there's a lot of terms here, huh? A1, A2, delta A2, delta A3, and so on. So now, actually, we have to look at the example only. You get the idea how I have explained just now. Okay. So now we look at this example. Look at example. After you have looked at this example, you get the idea how to do that. Okay. Okay. So now look at this example. Calculate the ultimate bearing capacity. Actually, is forget about the ultimate capacity and the what we want is the minimum nominal bearing length. Okay, we just, okay. The important here, we want to get the LB here. LB. Look at here from the edge here, not including the gap. Not including the gap here. The LB here is the nominal bearing length. We call it as a nominal bearing length. This is a nips. Okay, this is a concrete nips, and this is a beam that's supporting supported sitting on the nips here. So we want to calculate what is the LB. This is a dry bearing. Okay, means that it's just sitting directly on top of it only. Okay, and the width of the width here. Okay, the beam, the width of the beam is 400 mm. The width of the beam is 400 mm. And the end reaction here, is 300 kilonewton. Okay, 300 kilonewton. And the span of the beam is 6 meter. Okay, 6 meter. But 6 meter sometimes is not, you have to provide actually certain, the actual to get the LN. LN you have to plus a bit. Okay, 6 meter. And FCK 40 megapascal. And for the bearing, this one, you forget about this one. Okay, forget about this one. Mortar bearing here. You forget about this one. Cover to rebar in beam, and because actually this one supposed got two parts, but I just show it you in one single part only Okay, 40 megapascal. And also the cover, concrete cover is 30 mm. Okay, assume no bearing. Okay, just forget about this one. I think the redundance of the mortar bearing. This one FCK1I mortar bearing here, bedding here, mortar bedding here. These are actually, you just remove it. Actually, this one you have to remove it. Actually, this one actually no use. This one no use. In this example, I think no, we are not going to use it. Okay, and concrete cover 30 mm. No bearing, dry joint with vertical bend 16 mm. Okay, vertical bend 60 mm here. Okay, in beam and nips. So we want to calculate the LB. Okay, so we calculate the FCD. FCD is FCK divided by gamma M. The gamma M is 1.5. Actually, you can direct calculate the FRD. FRD here is equal to what? Just now, 0.266, is it? Because it's 0.4 multiplied by FCD. Okay, 0.4 divided by 1.5. FCD is FCK divided by gamma M here, divided by gamma M. Gamma M is 1.5, so it's 0.4 FCK divided by 1.5, or 0.266 just now multiplied by FCK, so you get 10.67 megapascal. This is the one FRD, just now this one. FRD 0.266, okay, 0.266 FCK. Roughly you get this value. Okay, 10.67. And the bearing width, just now I mentioned is B minus 2C, is it, or 600 mm, whichever is lesser. B, the beam width is 400, so the concrete cover is 30 mm. So 400 minus 2 times 30, this is given here. This one, the bearing width is B minus 2 times the larger cover, concrete cover. So, or 600 mm, whichever is lesser. Okay, so this is, we get the LW. Okay, we get the LW 340. Okay, so now after this, we try, in this case, it try this is a stress. The stress, the force is 300 megapascal. It's 300 megapascal. 300 kilonewton, sorry. So 300 kilonewton divided by, you want to calculate the stress, is it? The bearing stress. 300 divided by what? By the width multiplied by A1. Let's say we try A1. So A1 in this case. So in this case, you try A1 equal to 90. If you try 90, so basically the stress you get is 9.8. You get the stress is 9.8. 9.8 sigma ED here. Sigma ED basically is based on A1. Okay, it's based on A1 to calculate. So then after that, you calculate the sigma ED over FCD. Means 9.8 over FCD is 26.67 here. So you get 0.37. Actually, you try to counter check. If they say we are based on 90, I get sigma ED over FCD is 0.37. Is it 90 is sufficient or not? There you look at table 9.2. Okay, sigma ED over FCD. If we based on 90, we get, what is the value just now? 0.37, is it? 0.37. So 0.37, if you look at here, 0.37, actually, if you use 90 mm concentrated load, assume this the beam is sitting on that, is the concentrated load. 90, just now you use 90, actually you should less than 0.15. However, we get 0.37, is it? So it's between here. Okay, so now we try again using 110. We use 110. Okay, we use the A1 110 now. We use the A1 110. So now, not pass. We use A1 110 now. We try 110. So 110, if you 110 here, what is the value of sigma ED? You'll get 110. Okay, so sigma ED is 300 kilonewton divided by 340 times 110. You should get 8.02. You should get 8.02. So how to get 8.02 is basically 300 kilonewton divided by the bearing length, the LW. Okay, the LW 340 multiplied by A1 110. So you will get 8.02. 8.02. So sigma ED, you will get sigma ED 8.02 divide by FCD, then we check again, we get 0.3. So 0.3, 110 is between what? 110 is between 0.15 to 0.4. So 0.3 pass, is it? It's between here, so we can use A1 equal to 110. So A1, we got the A1 already, 110. Okay. And then we can calculate again, actually show you pass. So we calculate again the capacity, resistant capacity. Is this one, FRD, okay, multiply by the area. Okay, multiply by the area here, we get 399, which is greater than 300 kilonewton. So it passed basically here. This is the ultimate bearing strength. We check for the ultimate bearing strength. So the next one is we are going to get the what for what, the A2 and delta A2. Okay, delta A2 and delta A2. Is it this one 8.02 divided by 8.02 divided by 26.67? Okay, so okay, so now we go for table 9.3. Now we go for table 9.3. Okay, table 9.3. So basically table 9.3 here, concentrated load, is it? And FCK is with 40 greater than 30 concentrated load. So basically it's 0.3, is it just now? Sigma ED over FCD. Sigma ED over FCD is not 0.28. I think just now got made a mistake here. 0.3. So in between here actually is what you need to do is the delta A2 here is value is 15 mm. 15 mm. Then the delta A2 is 10 or L over 1200 must be less than or equal to 30 mm. Okay, so now we go and calculate. Okay, so A2, how to get 50 mm from table 9.3. So delta A2 is the maximum 10, okay, whichever maximum 10, maximum of the value 10 or the L over 1200. 6,000 divided by 120 is only 5 mm, is it? Between 10 and 5, so 10 will govern, is the maximum value. So 10 mm. So delta A2 is 10 mm. We got the delta A2 already. Now left only the A3 and delta A3. Okay, A3 and delta A3. Okay, A3 here, you have to refer to table 9.4. The vertical band bar is 16 mm just now given. So basically this is okay, we refer to table 9.4. Table 9.4. Okay. For concentrated load, is vertical loop reinforcement. We are actually using vertical loop reinforcement. Okay, so basically C plus R. C plus R, is it? C is the concrete cover. R here, RI here. RI here is the, actually you can, it's the band. So RI is roughly 2 diameter. So the bar is 16 mm. So 2 diameter is 2 times 16. Okay. So C plus 2 times 16. Therefore, you get the A3 here. You get the A3 here. A3. Okay. C plus 2 diameter. Therefore, you get the A3 is 62 mm now. Okay, 62 mm. So delta A3. What is delta A3? Okay, delta A3 is stated here. Look at here carefully. Delta A3, where is it already? Delta A3 stated here. Delta A3 for the length Ln of the supported member. Okay, Ln for the length Ln here of the supported member beam in figure 9.5. I don't know where it's given in PS. Okay, is equal to, important is here is delta A3 is equal to Ln over 2500. Okay, Ln over 2500. In this case, they assumes that the Ln is 6000 plus 150 6,000 plus 150. So therefore it gets is it? I think so You get 6150 with it. My okay, sorry, my slide hang Oh, okay, ready now. Okay, ready. Just now hang. Okay, so now the for the A3 ready. Okay, now A3 delta A3 is the length of the beam, but just now I mentioned 6 meter, is it? But there's a plus 150 mm. We assume you extend a bit. Okay, extend a bit say you say that this one is 6150 It actually is plus 6000 plus 2 lb over 2 So it assumes this one is say is 6150. Okay, it's assume it's 6150 We don't know actually the bearing length yet, but it assume it's 150 mm. Assume it's 150 mm Okay, so it's 6000 the actual, then plus 2 lb over 2 means both side is it, so divide by 2 center to center, you take it effective Okay, so assume this lb is 150 therefore you get 6150 here. So delta A3 is Ln divided by 2500. 2500 is fixed, so we get 2.5 mm. So delta A3 is 2.5 mm. So now we already get what? We already got the A1 is 110, A2 15, okay, A3 is 62, okay, and delta A2 is 10, delta A3 is 2.5. So the value is A1 110 plus A2 15 plus A3 62 plus delta A. Delta A is set delta A2 square plus delta A3 square. So therefore we get 197.3. Then the length that we need to do is to use is round off to the 5 mm nearest. So it's become 200 mm. Means that the LB that we need to provide here is 200 mm here. Okay, so the Q&A a bit so do you get it, class? So understand or not, class? Can you get it? Okay, so this is the way how to calculate the bearing length according to Eurocode according to Eurocode. For me it's a bit like complicated, you look at it, but at the end is to get the A1, A2, A3, delta A2, delta A3, delta A2 and delta A3 to calculate the set delta A okay, it look complicated, actually it's not that complex Okay, so now we now look at the, if let's say using Eurocode British standard, this is what I prefer. How we're going to do. Just one slide, actually, you understand the Eurocode 2, actually, if you go to use the British standard, actually is much simple. Okay, you look at the in this based on BSA 110, the previous code, British standard code here, but it's only the length and the width is opposite way. You name it opposite way. This is something like a plan view. Okay, you look at okay, I haven't shared the screen. Sorry, I have to share the screen first. I have to share the screen first. So now if we look at the in British standards, how it's going to do. Just now, the length, the bearing length is this one. This is the plan view. This is in the plan view. Okay, this is the plan view. This one is a supporting member, and this one is a supported member. Okay, some sort like that. Say this is can be the main beam. This is a secondary beam. Okay, this is a secondary beam. So this one is the width. Just now we name it this one as a length, LB, is it? Still remember? This is LB, this is LB, and then this one is LW, is it? The width. But however here is opposite way. It's opposite way. We name it this is the length and this is the width. Okay. So the length here, which is just now in the Eurocode 2, is the width, is the member, the size here, minus 2C, is it? Or 600 mm, whichever is lesser. However, in British standard, it's like this. It's also the least of the okay, the minimum value between these three parts. Bearing length per member, okay, means this one, this dimension without minus 2C, okay, or 1/2 of the bearing length member plus 100 mm, means that this one half plus 100 or 600 mm, whichever is lesser. Means that very straightforward. If this is 300, you just take 300, no need to minus 2C. Okay. Then for the bearing width, just now the bearing width we had to calculate A1, A2, A3, delta A2, delta A3. Okay, at the end only we can get the bearing width, is it? Which is just now it's bearing length. But however, now in Europe, in British standard here, actually it's very straightforward. How to get it is the bearing width is the design support reactions. Design support reaction means factor one, factor load, factor reactions, divide by the effective bearing length. Okay, effective bearing length is just now this one, is it? Is that say this is Gowan 300 bearing length here is 300. Okay, multiply by the design ultimate bearing stress. So what is the value of design ultimate bearing stress? It depends type of bearing. Maybe in your notes I did not provide this one. I don't know whether I could give you this one or not. Okay, for this is actually based on the British Standard Code. I just took out from the British Standard Code. For dry bearing on concrete, it mentioned actually is for dry bearing on concrete, the design ultimate bearing stresses are what? Direct bearing is a direct bearing. This is referred to dry bearing is direct bearing without bedding or bearing pit. Means just direct sitting on it. Okay, so we limit to 0.4 FCU, just 40% of the concrete strength. Okay, which is the design ultimate bearing strength. Okay, if let's say we have the material with intermediate bedding here, we got provide, let's say top up with epoxy layer or what, mortar layer and so on. So we limit it to what, 0.6 FCU. Okay, 0.6 FCU. And for, if let's say there is a steel plate, so it gives you some idea. For contact face of a steel plate cast into a member or support with each dimension not exceeding 40% of the corresponding concrete dimension. Okay, or 0.8 FCU lah, basically. This is how it limited. So means that if let's say for dry bearing, for example, so we just directly take it as a 0.4 FCU to get this one. Okay, and the bearing length is the width here. We know, we get it. So we know the support. So we get the what is the bearing width we need to provide. Then we round off to the 5 mm nearest. So what you get here, for example, let's say you only get the bearing width that required here is only 30 mm. You cannot just provide 30 mm. You have to provide at least 40 mm. Minimum is 40 mm. So bear in mind, minimum is 40 mm. Minimum is 40 mm. Therefore, if let's say go out next time, go out to works and so on, at least how much you're going to provide. Let's say it's not very critical. The member here is carrying just sitting on it only, no much load and so on. So you can say 250 mm, provide 50 mm at least. Okay, if let's say plus the gap everything, maybe you have to go for up to 75 mm. That is the minimum, the width lah, and so on. So this is in design of bearing according to BSA 110. Very straightforward. Actually, based on BSA 110, the example just now I show it to you is actually is just a single page only. We can finish out already the solutions, compared to BSA 110, compared to Eurocode 2. Okay, another type of joint that I have added here, I did not provide the calculations here. They're actually in the joint. If you look at the precast concrete design, joint here, actually there are many type of joint. Actually is what to say, it's a very huge topic. If we really want to study very in depth, we can actually many type of joint we can discuss. But I just selected a few that I think is important, especially for the bearing, for the corbel, nips, and maybe also the half joint. Maybe also the half joint. Okay. So shear here is something like this. If let's say this is a precast hollow core. In between one hollow core to one hollow core, actually you look at here, it is not flat. Actually, there's a key. There's a key here allowed to do the grouting. So in between these two member, actually is going to have a shear. Going to the shear. So this is a shear, interlocking here by shear. So we have to design for it. We have to design for it. But sometimes actually it become that is just a standard really. Okay, it is just a standard detailing. People are not proper design, not even go to design, maybe already establish it. So if you like this is the typical shear key that the connection detailing you need to provide. Okay, here some have some additional bar and so on. And this one, okay, this one is a shear joint. For example, let's say we have use the half joint here, half joint of the beam here. Then we slot in with a bar here. Slot in with a bolt lah. Okay, so this is also function can be as a shear joint. Is it? Let's say you pull here, so that is a joint. Okay, the assignment already posted, The assignment already posted. After this one, we are going to discuss the assignment. Okay, we are going to discuss the assignment here. Okay, so this one, the bolt here. So if we pull here, that is a shear joint here. Okay, in between here, there is a shear. So it's something like, okay, this can be a bolt or this can be a dowel bar here, a dowel bar here. So basically here will be, you're going to deform. But the failure here, if let's say everything are strong, the here, the bolt here or the dowel bar here will be subjected under shear as what you have studied before. Okay, you can design actually based on the shear capacity of the bolt. The shunt means this is a shunt here. The shunt, you can get the shear area, is it? Then you know the strength here, so you can go and what to say? You can go and calculate it. Okay, the shear capacity. Okay, so I think this one I did not provide you the example, but actually if you know the behavior without looking to whatever code or just go back to your fundamental that we have studied in the steel design, even you can design the dowel bar here. Okay, the dowel bar here. So now I stop presenting here, and now we go for the Q&A before we discuss the assignment. Okay, so any question class? One student did not join the class. The timetable, the attendance also already posted. So can you please uh, record your attendance? Record attendance here. Okay, record attendance. Remember to record attendance. Wait, I have to do touch out first. Okay, we have to touch out first. Clock out lah. Actually, we are actually work from home, but we still have to record our attendance. Clock in and clock out. So I have to clock out first because already 5 something ready. Okay, I clock out first. Sometimes they have to on your location where you are to do the clock out, clock in and clock out. Okay, so most likely I think after 14 we have to go back to office. Okay, I believe we'll have to go back to office because now the already allowed the to open, although it's CMCO places. Okay, the places that implementing CMCO, the school institution actually allowed to open. Okay, so those who are still not the final semester, next semester you have to come back lah. But for you, you all you are the final semester already, except you have to go for your industrial training. Okay, so now we go for the Q&A. Then after that, we'll look at the this assignment. Okay, the assignment. So any questions, class? Any questions? If you have any question, you can ask. Or if that say you are understand to what we have discussed just now, you please commentary. If you understand, you please commentary so I know you understand. Okay, not difficult actually not difficult. Okay, okay. So now we go for, you can now on the you try to download out the assignment. But I can share with you to look at the assignment. Assignment, no answer yet. Is very straight, open-ended a bit, but not fully open-ended Let me share the screen. Okay, so now we look at the assignment. Okay, I just prepare this yesterday. I prepared this one yesterday. Okay, I prepared it yesterday. Something like this. Okay, just look at like this. Something. The column size is 450 and 450, but not a big issue the column size. But the beam is, yes, the precast beam. That say the precast beam, the depth is 300 times 750. 300 is the width and 750 is the depth. Okay, that say this is the connections, but it's not practical. This one actually is not practical not really practical but that say we are going to combine using steel connection to support this this column, this this beam, join it to the column. Okay, I propose something like this. We have a boat We have a boat. Okay, we have both. Don't know one or two, I don't know. Okay, you are going to decide. Means, okay, this is just an idea, something like this. This is just an idea, huh? This is just an idea. Got any what message? Patented. Okay, so this is a side view, huh? But not necessarily this one is only two. This is only side view. It can be one, it can be two, it can be three, it can be four. If that say you view from here, how many we don't know. Okay, it's only here this beam here is giving you the length is 9 meter. Okay, the length is 9 meter. Okay, you can assume here lah, from here to here is 9 meter lah, huh? Okay, and the beam is carry a uniformly distributed characteristic permanent action, means GK and QK. GK is 30 kilonewton per meter and QK is 20 kilonewton per meter throughout the whole span, huh? And the GK already including the included the cell weight of the precast beam lah, huh? So 30 kilonewton per meter. So now, and this is a proposed joint connection that you are going to use an angle. Okay, this one is the angle. I don't know what is the size of the angle. On top also they are going to have an angle, maybe using the same size, but you are going to decide, you have to going to get what is the size, suitable size. Okay, concern few criteria is you have to know what is the force. Okay, based on ULS already. The joint you have to design based on ULS, huh? Okay, ULS, huh? Ultimate limit state, huh? Then after that, you have to know if both sides are the same. This one, you have to do some analysis to get what kind of forces here. It is not a rigid. Okay, basically it is not a rigid. It is a simple construction, huh? Okay, so you need to get all the size of the boat. Okay, the angle here, how many boat here. I just propose only, I just simply draw only how many boat. Okay, so you have to design, come out and then prepare the detailing lah, more detailed detailing with all the sizes from here, side view, that say you cut from here, how it look like and so on. Okay, so this is the assignment. Can you get it? Based on the above proposal, determine the suitable size of the steel angle, number of bolt, and bolt diameter. Draw the detailing of the connection for the final design. Okay, of the final design. So I open for the Q&A. If you have any question regarding the project. Okay, understand or not? Give you what is the time for projects. I give you stream was interrupt. Assignment 2, I think already posted, is it? Yeah, assignment 2 already posted. So you look at here, the assignment 2, upload the assignment in PDF format and turn in. So make sure you have to turn in after you do. Due date is next week, Tuesday. Yeah, we have the class on Wednesday. So Tuesday is the deadline, and submit in this Google Classroom. Okay, so can you get it, class? Can you get it or not? Understand or not? You got any questions or not? If you have any question, you can please type it, or you can ask. You can on the mic and ask. I can I try to open the another, or not the example. Any questions, class? If you understand or not the, okay, so it means that you have to think, you have to get it, think what kind of forces is, first of all, what kind of forces is going to resist by that connection. So every parts of the boat or the connection of the steel plate and so on, if let's say there is a shear, where which one is a shear, and then you're going to design lah, what is the shear force, if it is a tension or tension plus shear and so on, if tension plus shear, so you see how if tension plus shear, what is the equation to be used, you have to check back your this in your steel design, okay, in the steel design. Do you get it, class? Any questions about the assignment? Any questions or not? If let's say you understand the what you need to do for the assignment, so after that, sometimes you a lot of people after this will ask, okay, so you get the idea, know the instructions, what you need to do for the assignments. So please, when you do a calculations, you have to do some explanation about a bit of that connections. Means that is resisting what kind of forces, and in label it in which part. So therefore, you are going to design based on what standards, and then how you design it, the calculations, and finally is the detailing. Okay, so I open for the Q&A lah. I open for the Q&A if you have any questions for regarding on the assignment. If no question for the assignment, if just type no, then we'll continue a little bit for our lectures. Then we'll end out after that. So any question for the assignment? If no question, can you please type no? Class, nobody type. Do you have any question for the assignment? Why all quiet? Understand or not? Okay. Okay. Okay, Hui Ling got ask some questions. Wait. Okay, sir, is this related to bearing design that we learned just now, since we use steel angle for this assignment? Okay, actually for, yes, I can say yes, yes, a bit lah, If we want to get the bearing, you see the length of the angle extended parts, how much actually that one is a bearing, that one got related some of the bearing. So whatever information that not given, you can do your own assumptions. Okay, you can do your own assumptions. Okay, yeah, that one, yes, is you get from there is what is the length, minimum length here. Okay, you can use actually based on BSA 110. Okay, you can based on BSA 110 to do that one. Okay or not? Okay, I actually freedoms that one open. Okay, the rest got any more questions? Okay, So if no other questions, then we continue a little bit. We still got some time. Try to finish very short only, very short. Now we look at, okay, I share the screen first. Let me share the screen first. Maybe another 10 minutes, we can end out the class. Okay. Problem is here, why not go down? I just office this one. Okay. So we look at the part 2. Okay, so for this one is focused on the beam to column connections. Beam to column connections here. You look at here, you look at this picture here. You look at A here. If let's say you want to have a hidden, okay, a hidden here. So basically what we can do here is hidden here means that without the, can't see the connections are extended, something means it's probably this is part of the, like some sort like the beam here. What I can do here, the extend here means the beam here we can design something like a half joint here. Okay, we cut it like a inverted L here, half joint here. Okay, so we just sitting on here, the soft cantilever here. So this one is hidden connection. This is will come a hidden connections here. Okay, a hidden connections. Then B here is visible. Okay, if let's say we're using haunch or we're using corbel here, it's visible. It depends the type of building. Hidden sure it will be nicer, is it? Hidden sure it will be nicer. Okay, but effectively actually I can say corbel is more effective because we are not reduce the sections of the beam or the slab and so on. So now my concern here, we are going to look at the corbel. Okay, the corbel design. The corbel. So we just look at a little bit about the fundamental of corbel. What is corbel? Corbel basically is a short cantilever projection from the face of a column, which supports a load bearing on its upper horizontal leg. Means that it's a short cantilever projected from the column, and on top is going to support the load. On top is going to support the load. Okay, this one is under Eurocode 2 Eurocode 2. Basically, if we are using struck and tight methods, okay, we're using struck and tight methods here. So basically, this will be under tension. This under the compressions. Okay, we'll look at it later. I use more simplified way to do it. Okay, and it is usually extensively in situation where the visual aesthetics of connection is not important. Means that you look at here now, you come out because it is it's visible, is it? Therefore, in terms of aesthetic, it's not important. We can use a corbel. And the reinforced concrete corbel we can classify as shallow corbel and deep corbel. Okay, shallow and deep corbel. And the shallow corbel, where the distance to the effective position of the load action AC. Basically, this is AC. This is called AC. Actually, this is also the shear. What is it already? Shear length, is it? I think it's shear length, is it? Okay. Okay. AC. This one is less than or equal to 0.5 HC. Mean HC is the overall depth of the this concrete corbel of the corbel. So AC is less than or equal to 0.5 HC, and approximately about 0.545 D D is here. This is the D Okay, D is from here to the reinforcement here. Okay, because tension is on top. Okay, this is bottom part is a compression. HC is a total depth. So actually there's some guidance here for us to provide the sum of the dimension here, for us to provide the dimension. What is the some news here come out? Okay, so and the leak length here, A is less than or equal to 0.7 C. So what is A? You get this is the leak length. Okay, is the A is the leak length here, the total here is given some guide actually based on some guide FIB 214. A is less than or equal to 0.7 HC, and AC is 0.4 to 0.6 D roughly. Okay, and AC is less than or equal to HY also. HY, this HY also. AC also less than equal to HY. These are the sum of the requirements, okay, if based on this standard. So when we propose the dimension of the Cobell, so these are the things, these are the things. Okay. So if that say the dimension is not comply, the short cantilever is not comply some of the as what I mentioned. So you will become you have become qualified as a NIPS ready. Okay, the width of the Cobell must be less than about 500 mm. Otherwise, it qualified as a NIPS. After this, we'll look at the NIPS here, how design for the NIPS. So this is called shallow Cobell. Okay, this is shallow Cobell, and this one is the deep Cobell. Okay, this is about typically is actually this height is half. Usually we propose this half. Let's say this is 500, 250, 250, and this one also is become 45 degrees. So you get what is the dimension here, okay? And this is about 70 degree typically ish when it is this is a chamfer, okay? Then 70 degree. So we get the overall depth here. So you look at some picture. This one is a single side. Here, one side, Cobell. Okay. And you see the reinforcement actually inside here. Inside the Cobell actually here, the reinforcement, how the detailing here. Okay, how the detailing here, okay, get some idea. So this one, if that say is both side, both side, both side, left and right. Actually, we design one. If that say it's the same, it's symmetry, we just design one and they propose for two design used for two both side. But the reinforcement just extend out. You suppose it's bent, but it just extend out here, become a loop. That's for both sides. Okay, so I think for coming one, we are going to discuss how the design. We got the example after this. So all this we will discuss later. We have to refer to the handout and then we will design for the NIPS. We got the example in the giving you ready. Okay, so I think today we stop here. I stop here. If you have any questions, so please you can ask. Okay, so any question? So class, give some idea, you get some idea how you get the about the Cobell, especially the Cobell. Okay, so any questions? If no questions, if you are no questions, so we are going to end out our class for today. So remember to submit your assignment on time. Okay, individual assignment. This individual assignment. I hope that your also your projects. Your projects. After that, I will prepare a link and also the rubric. Rubric form for the projects that you need to submit together. Okay, for the projects, I will let you know before when it's going to submit and how to do the submission of the projects. Okay, so Any questions? So if you are okay, happy with today lectures, no questions also, you just comment 6, then we'll end out our class for today. Okay. The rest,